content and what is style are not easy to describe functions. Right? I mean, right? So what is the sequence is the interest, and what is the Michelangelo sculpture, and what is Van Gogh's paintings, etc. is style, are not easy to describe functions of the pixels. Nevertheless, generative models of the present can be leveraged to do all this kind of stuff. And this can be very important in applications called inverse problems, where certain aspects of the content you're interested in might be missing. Okay, so for example, like maybe like the type of access you have to the object of interest might have some various types of corruption, making the content inaccessible. So you can use the prior that these models have learned, trained on good samples, to recover the signal that is missing. This is similar to what the brain does, the human brain does. So the human brain has a lot of experience with good samples. And when you have a bad sample, when it encounters a bad sample, it uses all the prior that it has to reconstruct what it thinks is the good sample that gave this bad sample. Right? You walk into a club, the lights are dim, you meet a person, you can't really see them, but you have experience with crisp images of faces from your experience, and you can reconstruct the missing details and so on and so forth. Our brain does it all the time, we don't even understand it. A lot of the stuff that we're perceiving actually is reconstructions from bad samples of some underlying truth. But of course, what our brain reconstructs is not the underlying truth. It's just
bad sample is like poor sample, incomplete sample.
Incomplete sample,
also missing.
Yeah.
All the time for reconstructing what is behind behind the object, etc.
Yeah, all sorts of missing information. So here you see some examples of that. So these are just linear corruption. So here you're missing part of the image. Here you have done some Gaussian blurring. So you have a Gaussian experiment that move around the image and you average the samples, the pixels in the little squares. But these are some non-linear stuff. Here what you do is you take the type of missing information, sort of like you do the Fourier transform of the image, and then you keep the frequency information. You only maintain the amplitude. So basically you lost all the phase in the Fourier space. But you can use your experience from from other good samples to increase the missing information. It's a nil-pose problem, right? Without the prior, you cannot solve it uniquely. But you can use your prior to output the sample from the posterior distribution. And there's some samples from the posterior under various different types of missing information. Of course, you can also use it for Photoshop style applications, right? Like here you have an image, but we really don't love this stop sign. So you just crop it from the image, right? And you ask the model to just in-paint the missing information. Now the model pulls from its experience from good samples what could be there. And of course, a stop sign being there is a low probability event, so chances are it's going to be removed, and some, what is going to be paint is not going to be the stop sign. Okay? So, and stuff like that. Yes, here the varies from the tree. You want to remove it. Okay, maybe there's still a chance that you see a tree there, but if you sample a bunch, maybe you do not see a tree, and so on and so forth. So you get the picture.
For people we move on, you need, as you mentioned, some example from closed systems, some examples from open systems. globally today for these kinds of applications, how can you compare performance of these categories? More and more important politically.
Yeah, that's an important question. I think open source, I'm a big proponent of open source. Especially, when you want to use a model for important downstream applications. You want to know what data it was trained on, because the data is going to reflect biases that the model will have. You want to be able to inspect, do all sorts of different tests that you want to do on the model. If it's a closed model, you only have like black box access to the model. It's very hard to run these tests. There's a whole, politically, there's a whole discussion also in Europe around, open source and closed source, and what exactly the regulation would look like.
But for the performance now?
It's not like so performance is not a matter of open source versus closed sources, but it's more of a matter of how much compute you have to train these things, and how cavalier you want to be about using data. Okay. So if you're like a company that has a lot of funding, you can use a lot of compute to train your model, and also whenever somebody sues you for bad use of data, you can settle it and be done with it, right? If you're open source, you have less data, and also it's unclear exactly how yeah, I don't know. Okay.
You have to be more cautious about the legal issues.
Yeah, exactly. But in terms of performance, the moment models become open source, there's a lot of progress by a community of scientists working on those models. And it definitely, I don't think any company has a lot of secret recipes. In terms of the ingredients, algorithmic or otherwise, that you need to train these models, I think they're pretty diffused now in the community. No secret sauce. It's a matter of resources. Okay. And of course, how cavalier you are about the data. An important application of diffusion models is in the scientific domain. And one example is their use in protein folding. Both in terms of generating new folds. So these are examples of a generative model proposing de novo protein structures that you can look at and see, hey, is that a nice structure? Can I use it in some application? And then you can investigate, what is the sequence that, the amino acid sequence that could give this structure. Or perhaps you're interested in a particular sequence. You have, part of the sequence of the coronavirus, and you want to fold it to see what kind of structure it has. Okay, so this is the equivalent of sort of this is sort of conditioning on the sequence. I want to find a fold. This is what AlphaFold does. This is, I don't have a sequence in mind. I want de novo structures. And if one looks interesting, you can try to see what amino acid sequence might have given this structure.
It generates rather than analyzes, this one?
Yes, this one generates, and I'll talk about in the second lecture I'll give on Thursday. We're talking about some progress in this space. These are samples from a model that's called Proteina. In some recent work that I've done, we have new models that are actually as good or beating Proteina on this task. And I'll explain, where the progress is coming from, and it ties well to the contents of this lecture. Taking a step back, a lot of the progress in generative models and more broadly machine learning, deep learning, comes from the availability of data. Okay, so it's not an accident that like all this progress happened over the past decade, but because the preceding 2 decades came with the internet and all the data that was collected and stored there. None of the progress on the model side would have happened if we didn't have access to the data. When you have good data, you can build good models. And as I said earlier, like sort of like in terms of like the technical, of course there's progress on the technical front, but sort of like the ideas are out there. So now if you're a company and you want to build your model, if you have good proprietary data, you can get an edge. If you're at a university and you have access, you generate good data, you can get an edge in terms of models. So data has become, as they say, the new oil. Okay, so data is super important. So in other words, like I guess just to summarize what I said, at this point, the main moat you can build around your company or your research is the data, and less the models, the technical aspects of how to train the models. Which brings to the other point I wanted to raise, which has to do with that sort of like data can be a bottleneck. In many applications, especially in the scientific domain, data is the bottleneck. And here you see some examples of these domains. One is MRI, reconstructing high resolution MRI scans from like a small number of measurements, protein folding, and images of the scar, these images of a black hole. In many of these applications, you actually don't have, either it's very expensive, or it's essentially impossible to get very good, very high resolution data. So in an MRI scan, to get good high resolution data, you need to have the patient stay there for a while, which of course is not nice for the patient. And also it's going to overuse your machine and stuff like that, right? So there's a lot of reasons why you don't want to have the patient in the machine for too long. So, and sort of like if you want to train, so what do you do then? So what you want is the model to reconstruct. You want to give the model a low-res picture of an MRI scan, and you want the model to give you a high resolution image. But how are you going to train a model that outputs high resolution images if you don't have the high resolution data to train it with? And getting those is very expensive. Okay, but at least it's feasible. Okay, you can in principle have, I don't know, 1,000 patients stay in the machine for like 2 hours to get some like really good data. So that then for all subsequent patients, you can do, you can train their model and then do the super resolution. But like sort of like for images of the scan, so we have about 7K, we have like super high resolution MRI images.
That's really interesting because the example of MRI is the one that Emmanuel Candes used in his 2014 ICM lecture, which was first time at plenary ICM. It was discussed AI, and he did not use so much training. It was sparse sensing. So reconstructing lowest range matrix behind the thing.
That's a great point, and I think maybe I get the opportunity to paint a picture of like classical approaches and like sort of like new age approaches. So the classical approach to MRI, and super impactful, already like all sorts of medical machines that are used in hospitals, is what Cedric is talking about, which is the sparsity-based approaches. Okay, so effectively, so here's what's going on. So effectively, the MRI image that you want to reconstruct the signal is a super high dimensional signal. And when you put a patient in an MRI machine, you take a few linear measurements of the signal. So think of like, this high dimensional signal, and think of this matrix of measurements as a fat matrix. Okay, so like you take a small number of linear measurements of this high dimensional signal. So effectively, your measurements, which is like a small number of measurements, is Something like this. Okay, so last noise. This is low dimensional, this is high dimensional, this is low dimensional. So now what you observe is this, when the patient comes to the MRI machine. But what you want is this, which is a high dimensional signal. This is an impulse problem. You cannot, there's no unique reconstruction of X satisfying this. I mean, even just yeah. So let's ignore the noise now. Okay, so just to not confuse. So this is an imposed linear system. So what are you going to do? There's no way to uniquely solve it. So you have to use something about what you think is the real, some property that you think real the signals from the real world satisfy, right? And the assumption is that, look, X's, like real brain images, are not arbitrary signals. That, they have some structure, and maybe if I leverage that structure, it's okay to use a smaller n number of measurements, and still be able to reconstruct this big signal. So the standard assumption that people make, and again, this is already incorporated in medical machines, is to assume that the signal you want to reconstruct is sparse in some basis, okay? or close to be sparse in some basis. So particularly assume that, for example, like the Fourier transform of X, or the wavelet transform of X, or something like that, okay, has a small norm. So some norm of the Fourier transform is small. For example, we assume that the Fourier transform only has a small number the sparsity of is k.
The first possible non-zero components or something like that.
Yeah, so let's assume, right, so you assume that the Fourier transform of your signal is a vector that only has, is a bunch of zeros, and it only has a small number of non-zero entries, like k, which is much smaller than n, which is much smaller than n. Okay? So now, if you are in this kind of scenario, like if you're okay making that assumption, then this is not an imposed problem anymore, and you can solve it. So this is the classical approach. It doesn't use any data, right? No training. It only makes this postulate that some sparsity is satisfied by the signal in some basis. The new age approach is to say, look, perhaps I can use more than just this. Perhaps I have access to some samples that are very high resolution. Like, for example, maybe I have like a few thousands very high resolution images from MRI scans. And I can train a model that understands that distribution. And now that I see my small number of measurements, I can say, look, I can try to output an X hat from the posterior distribution given to measurements. So I'm leveraging more than just the sparsity.
You can combine.
You can combine them. Yeah. And you can get more leverage out of the access to the high resolution images. So that's a new age approach. But back to this point, as I was saying, like, if you want to pursue that sort of like direction, you need some good signals to train on. And for many scientific applications, like in MRI, in protein folding, in images of the sky, these are very expensive or impossible to get. And that sort of motivates part of my course, as I will discuss. The other reason having access to good data might be bottleneck is that in reality, you know, like even in situations where you have a ton of data, these data do not have the same quality. Like if you look at images from Flickr, some are higher resolution images, maybe from photographers. But you know, like the rest are from all of us, and they have a lot of artifacts, like overexposure, motion blur, and so on and so forth. So like, even in situations not scientific, like MRI scans or proteins or images of the sky, but like even like everyday images posted on the internet, they have a lot of artifacts. That doesn't make sort of like data from the internet of the same quality. And as a result, any pipeline that trains models first does a filtering step, where you take all the data that you have access to, you run a bunch of filtering steps, and you arrive at a smaller data set than what you started with. And here are some numbers, right? So like, I'll discuss proteins later in the course, but like, for example, just one of the main data sets for training image models would ultimately throw away 70% of the data that you have. Like, this data from data set downloads all the internet. Think of it as downloading all of the internet and running a bunch of tests to keep on with the good samples. So you throw away 70% of the internet if you want to arrive at reasonably good quality data to train it on. Okay? So you throw a lot of information that you have access to.
I agree, it's a lot, but still it's not as if you were losing 99% or so. I mean, the order of magnitude remains roughly the same.
Correct, yes. And finally, like, coming back to your earlier question about like, sort of like, being cavalier, not about the data, the truth is that these models do memorize a lot. And here are some examples that we run in a paper, where we took stable diffusion XL, which is one of the main, most prominent diffusion models. And we took a bunch of images that we suspected might have been used in training this model. And we just wanted to see, okay, like, how we run a test to, see if this were indeed used in training. So what we did is the following: we took images that we suspected were used in training. We put 3 black boxes on interesting aspects of these images. Like here, we put a big black box on the head, around the head of this person. Over here, we put a black box around the girl that is watching the game, and so on and so forth. And then we said, okay, like, we asked stable Excel, okay, can you help sample from the posterior? Okay? And we got the exact same person. Okay? So of course, like the likelihood of getting that same person was small. The fact that we got it probably, suggests, that it was used in training. And sort of like
the only one, the third one is not.
The third one is not.
It's not completely conclusive.
Yes, it's not conclusive. And like I mean, like I don't know, maybe even this one is this one. So maybe you can say, okay, like this kind of. I don't know, like knife in England, but like maybe say. This is maybe stuff on charge. Anyway, so the point is, so because of this memorization, and privacy violation aspect, it does make sense that that's another reason why even if you start with high quality data, you might want to add noise to them to avoid this kind of privacy violation thing. For example, like as in Google Maps, they put like whenever they see a face of somebody, they put like the pixelate their faces or like the blur their faces to avoid violations. So like for example, if you want to train on Google Maps images, you have these issues that parts of the image are going to be blurred and stuff like that. So long story short, this is kind of like the state of the art, and some thoughts around data and issues around data quality. And here's the plan for this. These are the goals of my class, and and then I'm gonna discuss the plan. So what I want to discuss is the basics of diffusion models, which are a very prominent type of generative models these days. I will talk a bit about the mathematical foundations. And I will discuss what to do about data. Okay? In particular, I want to discuss how to train models that are state-of-the-art, even when you don't have access to good data. My expectation when designing these slides is that you are familiar with the basics of stochastic calculus. Some of you are definitely better than me, more knowledgeable about stochastic differential equations. I will not be pedantic because that will slow me down, but I expect you to fill in the details. And my hope is that, in my experience, mathematical insights can be effective in designing important practical methods, as I will discuss. And I hope that I will exemplify a direction where mathematical intuition can be important and have impact. And my plan is this. So I want to talk about the basics of diffusion models. I want to talk about how to train them with low quality data. And I'm going to give, maybe next lecture, applications to protein forming. And let's see where we get. Please interact with questions, even if you don't finish the whole thing, it doesn't matter. Okay, so the basics of diffusion models. Okay? So here's the goal. You have a lot of samples from this V0. V0, think of it as God's distribution. So God is sampling this distribution, and it's giving you samples from it. Okay? Like all the human faces that you have ever seen are samples from God's distributions. All proteins from which you know the fold are examples from God's distribution. This is an ideal distribution. It does not have a parametric form. It's not a nice distribution. If it was a Gaussian, you could estimate the mean and the variance and be done. Okay? But this is not a nice distribution. It's high dimensional, and it's multimodal. It's not nice. Our goal is to identify an algorithm that samples from that distribution of which we only have sample access to. Okay, so how are we going to do it? Okay, so our goal is not to learn the parametric form, is not to put down a parametric form of the distribution and find the parameters of this parametric form. Our goal is to directly come up with a sampler for this distribution. Of course, we will actually learn some aspects of the density, but I'll discuss that in a bit. So what is the approach here? The approach, the main idea is this, that look, this distribution is ugly, multimodal, not nice, but...
It's the work of God, you cannot say it's ugly.
Okay, good. But, if I convolve it with a Gaussian distribution, with large variance, I'll make it nicer. Okay, so maybe Gaussian distribution isn't ugly, but convolving Gaussian distribution with a Gaussian makes it prettier. So maybe for this distribution, the convolution of Gauss with a Gaussian with large variance, that's definitely a nicer distribution. It's more smooth, it's less multimodal. Perhaps it's easier to find a sampler for this distribution. And maybe if I have a sampler for this distribution as a warm start, I can work my way towards getting a sampler for the distribution that I really care about. So to implement this idea, here's the plan. So we're going to construct a sequence of distributions with growing levels of variance according to some noise scale. So we're going to pick a noise scale. And we're going to consider this family of distributions from 0 to some capital T. So let's look at them. Okay, so this is the ugly distribution. And these are progressively smoother versions of it, involving this with Gaussians of progressively increasing variance. And the plan is this, right? So like, let's look at the nicest of them. Like it almost looks like a Gaussian. Like this is a unimodal distribution, very nice. So maybe that's easier to learn a sampler for. And if you have a sampler for that distribution as a warm start, maybe we can get a sampler for the distribution that's just adjacent to it, like a little bit less nice. Okay, so here it's pretty nice, a little bit less nice. And then if we have a sampler for that as a warm start, maybe we can get a sampler from that, and so on and so forth, down to the distribution that we really like. We're going to work our way down to, yeah.
There's a naive question, but obviously you tend to think that you are going to learn the Gaussian distribution. That's what you're going to learn. How does it make it easy?
Are you asking if this looks like a Gaussian? There's still some Pinot signal here. It never becomes like exactly Gaussian. Like, are you asking me why I should expect this to be easier to?
Yes, well, it is easier. Obviously, it's easier because it's more normal. But,
it's easier because it's it's like at the very least you give me that it's unimodal, right?
I will reformulate part of the question of François.
Yeah.
We know in statistics, quantity which tells you how much information you can construct for observation is the Fisher information.
Yeah.
And Fisher information is minimal for Gaussian. In practice, Gaussians are those for which it is somehow most difficult to reconstruct the parameters in a way. So the idea that starting from this is easier, okay, we see that it's nicer and so on, but in itself, from a statistical point of view, it doesn't tell you why it is easier to reconstruct the parameters.
Right, okay, so there are two questions here. So one is like the information theoretic aspect, and the other one is the algorithmic aspect. There are two different aspects, okay? Algorithms, like unimodal, local cave, etc. distributions. Of course, I'm destroying my signal, right? Like if I take a lot of samples from this guy, I have nice images, and add a ton of noise to them, I destroy the information. Okay, so statistically speaking, I'll make my life harder. Algorithmically speaking, I'll make it easier. And the hope is that there's a trade-off here that I can exploit to effectively solve the algorithmic problem. Right, and the algorithmic problems, the root of the algorithmic problems is that sort of like I don't have a nice parametric form of this guy, and I don't know what to postulate for a parametric form. So what I'm going to do is I'm going to think of this family, and then sort of like get algorithmic leverage by first targeting a nice unimodal distribution and working my way down as a world start down to this one.
May I say something?
Yes, yeah.
The goal here is not to learn the final distribution, it's a Gaussian. The goal is to learn the flow. This is the goal. And if you learn the flow, and if the flow is invertible, this is exactly what was said, and we're going to go on.
So perhaps
this is my understanding. You learn the flow.
So we'll see what you learn, yeah. So there's going to be some invertibility and stuff like that, but like I think like it's important to think of this trade-off between information, I have destroyed information, and algorithms, which like unimodal, and the trade-off between the two, and we're going to get like I can quantify a lot of things in a bit. But for now, let's leave it at this and come back to the
final question. Sorry.
Yeah.
To that even more. The whole sequence of data you will use, right? So you start from an initial set which is like this, and then you prepare it in a way that it's like this. And you even have much more data.
Exactly. In reality, I'm not going to, as we're going to see, I'm not going to throw away any of the data. So I'm going to use, I'm going to simultaneously train something for all these intermediate steps. So it's not like I'm going to take my data just to construct data of this guy and throw away everything else. Okay, so as we're going to see, I'm going to keep data for all intermediate distributions and simultaneously train something together. So effectively, no information will be lost.
But it also.
But still, I will focus my algorithmic attention. Right? So I'm going to spend time on all these times. So I am dividing my algorithmic attention among all these layers, right? So, algorithms like this, there's less information there. There's more information here. I'm dividing my attention, but the trade-off works out well. Yeah.
You know this better than me, but people from the sensorial theory, they say that we see things at various blurring levels.
Yes.
People like David Marth and so on, they work on this multi-resolution scale using without noticing.
Yes. Yeah, so I mean, this is essentially what's going on here. But it's pretty much what we talk about. This was like effectively like sort of like the distribution here. The distributions at higher times effectively kill the high frequency aspects of the image and maintain the coarse information of the image. And the information, the distributions over here, like as you go from here to here, you effectively are filling in higher Fourier coefficients for your samples. And I'm gonna revisit that. Remind me to talk about it. You can make this precise. Effectively, okay. So here's an empirical fact, right? So if you take, and in fact, interestingly, this holds sample per sample, or at least for the average sample. If you look at, if you take a sample and you look at the, you do the Fourier transform of the sample, and you look at increasing frequencies, and then you look at the amount of energy that you put on different frequencies, you see something like that in log plot. So effectively, like as you're adding more and more Gaussian noise, you're effectively like keeping low frequency information and tapering off the high frequency information. Okay, so this kind of like whole sample per sample. So this was happening there. So like the more noise you add to a sample, the more you're killing the high frequency information contained in that sample. You're keeping the high level information. This is important intuition to remember as I'll talk about later about low quality data. Okay, so let's look at a sample. Okay, so this is a colleague of mine who works in computer vision, so sometimes I use their image. So
if you ask permission to involve
this is a sample from God's distribution, and this is like the specific sample with increasing levels of Gaussian noise added, support the Gaussian, added to the pixels. So if I look at some intermediate time t, that sample is a convolution, a sample from like distribution controlled with the Gaussian, not this sigma t variance. There's a particular one way to produce the sample is to just add an isotropic Gaussian to it. I hope you can see the red. I apologize for the red. Can you make up the red back there? Yeah? Okay. It just says sigma t squared. Okay, so as you know better than me, one way to generate all of the samples together is to write a stochastic differential equation, a diffusion process, where this GT function is the derivative of the variance schedule that use to define these distributions. Okay, so if you run this SDE, you will get starting from a sample from Timo, you will get together the whole trajectory of samples that you see here on the screen. That's the Brownian motion height, different trajectories from the Brownian motion. And here's an example. Sorry, I mean, I wanted to, oops, I messed it up. So I wanted to, give just a concrete example, right? So like, if I want the variance at time t to just be t, then, there's no coefficient there, the relations are simple. So this is a concrete example of what I wrote before. So, right, so like I'm flipping between the two, right, to see the, right, so if I want sigma t squared, a little bit uglier. If I want just t variance, then it's nicer. Okay, good. Now, so the beautiful fact that we want to exploit here is the fact that SDEs have reverse processes that are also diffusion. Like diffusion processes have reverse processes that are also diffusion processes. So let's think about that. So here I have basically at time 0, I'm thinking that I have a noisy sample that I call y naught, do not confuse with the x's. Okay, so y naught is a noisy sample from Pt, the Pp naught convolved with the Gaussian of the highest values that I'm considering, sigma capital T squared. And at time t I have a free sample. Okay, so, right, so in particular, at time capital T minus little t, right, so I have a sample from Pt. I didn't do anything. Okay, so the beautiful result that I was talking about is that this process here is also a diffusion process. Like the reverse, like starting from a noisy sample and hitting a clean sample. This is also a diffusion process. A little bit uglier diffusion process. Okay. In that, I mean, I don't know if it's not, like in that there is a drift. Okay? And what is the drift trying to do? It is the gradient with respect to x, the inlet space, of the log likelihood of the sample. And what is it trying to do? So it's trying to push the process towards increasing the likelihood of the sample. Okay, so you want to go from like a noisy sample to a good sample. So of course there must be some drift that pushes you into higher likelihood samples. So this, right? So this is the modification that that you need to make. So that the cool fact is that this is still a diffusion process. So you still have Brownian motion driving it, but you have this drift. Again, this GT function is just the gradient of the noise control. Here, since this is a class, I decided to just throw in exercises for what I wouldn't have time to cover. But like, if you haven't seen, this functional form for the reverse process, try to derive it using the Fokker-Planck equation. If you don't know what the Fokker-Planck equation is, then let me just say this very, very, very briefly. It characterizes the density, the probability density function that you will see at time t of the diffusion process. So you have like a general, so here I'm considering a more general diffusion process with a drift term that will depend on both x and the time. And a valence term that again will also depend on both x and the time. And if I want to look at different times t, what is the probability density function then follows this differential equation. This is what the Fokker-Planck does. So the way you use the Fokker-Planck equation to see that this is the reverse process of the one that I was talking about before, with the x's, right? So is to apply the Fokker-Planck to the x equation, apply the Fokker-Planck to the y equation, and look at sort of like and see that the distribution of this guy is the same as the distribution of xt. Okay, and this is how it works.
Now there's
and then the uniqueness. And
but there is a big catch in the sense that the forward one is typically a linear equation, linear PDE, and the backward one is typically non-linear one because the density is in the spot function appears there in the form of the equation also.
Sure, because there's no mu, right? There's no mu in the forward. There's no mu, there's no drift. Well, here there is a drift, but these equations are not very hard. Like this proof is not super hard.
No, but I mean that the form of the drift will depend on the function itself, on the measure itself, which makes it non-linear or coupled in this way. You rewrite an equation which was linear but unstable because backwards into another equation which makes sense but is non-linear, if you see what I mean.
Sure, but I guess...
I don't say there is more of that, but this is what makes it... Because first it's shocking when you see it first this way, but then when you think that you lose something and you have a trade-off, you rewrite it as a diffusion equation, it's not one thing, but with the drift, that depends on the measure itself.
You're talking about the drift here?
Yes.
The drift here, it does use the measure. Yes.
So if you think of it as a PDE, it will be a PDE which the drift itself is coupled to the whole distribution, making it a non-linear coupling.
Yeah, that's right. But in the proof...
in the proof you don't care.
Yeah.
It's just a chain rule.
Okay, here's the instantiation for like the variance T case, just for comparison. I don't know. You don't have exactly GT terms. Nice, simpler version. Sorry about the red. Good. So and now sort of like okay, like I flipped again the times. Now sort of like I rewrote it in terms of x again. So I flipped the times between here and here. So I replaced y's with x, yt with x t minus 2, and the resulting equation is this. So now like both differential equations refer to the same variables. Okay, so sort of like like the x's satisfy two differential equations. Okay, one is the original one, which you don't see, but it's this one. One is this one, initialized at P naught. And the other one is this one, initialized at Pt. And now, here you see Brownian motion, shown at the top. And over here, because I did this like time reverse, you see the reverse diffusion process. The reverse Brownian motion. Okay, so it is 0 at capital T. And like as you go backwards in time, we get variance. I just did some change of variables, so this didn't do much. But like now you see everything. Let me see. Okay, I'll show you a summary in a sec. But okay, so far so good. now here's what we want to do, right? So how do we plan to sample from P0? The plan is the following. We want to estimate the score functions of these gradient log likelihoods at all t's. This is the thing that we're going to estimate from samples. I'll show you how. If you have estimated this guy, that for every t, the gradient of the log likelihood of the density of that t, if somehow you estimated that, then you can start from a sample from PT. I'll tell you why, because we don't even have access to PT in reality. I'll tell you what we do. But let's say we did. Okay, so you start with a noisy sample from capital PT. And then you're going to run the reverse diffusion process. The only thing you need is the scores. And then you hope to arrive at the sample from P0. This is the plan. Again, there are details. Okay, so one detail is I don't really have access to PT. Right? I mean, PT has all the information of P0 in it. Right? So, like the Fourier of PT is just the Fourier of P0 times the Fourier of the Gaussian distribution. Right? So, everything about P0 is in PT. So it's not like having sampling access to PT is an easy thing. Okay? But what am I going to do? So I'm not going to sample. In reality, I'm not going to sample from PT. I'm just going to sample from the Gaussian distribution. Okay? The other thing that I'm going to do is that I'm going to estimate the score function. I'm going to make some errors. Okay, so there's going to be some error in estimating the score function. And finally, I'm not going to run the continuous reverse SD. I'm going to do it in discretized. So there are three sources of errors that are coming in the picture. One, again, I don't have access to PT. I'm going to replace it with a Gaussian. Two, I'm going to have errors in estimating the score. Three, I'm going to discretize. You can basically quantify the impact of all of these errors in terms of total variation distance of what you're actually sampling versus what you want to be sampling. And you can contain all these errors. You can quantify exactly what the impact of all these errors is.
In practice, from your experience, which is the A, worst, and B, most difficult to control?
I think the score function estimation is the important. Yes. Because how many samples you have and so on and so forth will dictate how well you can learn that. Now, but yeah.
I just said before that we learn the flow. In this particular case, if you learn the score function, this is what you want to do and this is what you see.
Yeah.
You learn the flow because so the point is to learn the score function.
The whole, what you want to do here is learn the score function, okay? And how do you estimate the score function? It's not an easy thing, right? I mean, how the heck are you going to learn the score function?
It's from at the start, one doesn't see why you think the score function would be easier than the whole thing.
Yeah, exactly. Like, why is it, this is still like the gradient of the log likelihood. Why is it an easier thing to do?
If you don't know the product, you don't think it's more difficult than the original one because maybe
it's the gradients of a bunch of things.
the gradient of something.
So here's the thing. Here's the beautiful, not hard to prove, but beautiful thing. The score is intimately related to a denoising operation. So the score, the gradient of the log likelihood at time t, is effectively this is conditional expectation, minus x divided by sigma. But the interesting part of it is this conditional expectation. So the score is called Tweedy's formula, which was communicated to Robbins statistical powers in 56. For something different, like for correcting for certain types of selection bias in any statistical estimation. But the beautiful aspect of, so this comes from the fact that we're doing Gaussian convolutions, right? This is all it needs. It's not hard to prove, but the score at level t is literally asking, given that x equals x, what is your best prediction of x naught? Minus x divided by sigma. Okay? This is what the score is.
Has to do with the
function. Yeah, so it's coming from the functional form of the Gaussian distribution, right? Which suggests a very simple way to estimate the score, which is to write this loss function, right? So to say, look, I want to estimate this guy, right? Given some x, I want to be predicting x naught. How am I going to do that? Well, I'm going to train a neural network that takes us input xt and tries to become as close as possible to x naught. So I'm going to, take a bunch of samples from x naught, my God's distribution. I have sample access to God's distribution. From each sample from x naught from God, I'm going to create xt. I can do that because that noise. And then I'm going to tell my neural net, hey, here's xt. Try to reconstruct, denoise it, to become as close as possible to x naught. The ideal optimizer of this loss function is obviously the conditional expectation, right? I mean, like, the effects theta, if this function was arbitrarily expressive, the optimizer of this, the variational problem that I'm written there, like that, if optimals are all possible functions, the best function is this. Okay, so my neural net is going to be complex enough, but hopefully it's going to approximate this area.
And I see that the problem is you have big parameter space theta and functions, so that H is a bunch of functions dense in the set of
Yes.
functions depending on theta. And you
Yes.
don't really worry too much about what is the precise dependence as long as there are enough functions H theta.
Yes. There's going to be some big enough neural net that I hope is expressive. I mean, there are a lot of approximation theorems for neural networks and stuff like that, saying you can effectively approximate to arbitrarily good accuracy if you increase the. So I'm going to pick a rich enough function twice, and my hope is that I'm going to get close to And in fact, I want to learn it at all t's. And I want to borrow statistical power from like some t to some t prime. So in fact, what we do in practice is we have a neural net that takes us into two things. Right? We have the parameters of the neural nets have theta, the parameters of the neural net. Now, the neural net takes two inputs, xt and t, what t we're talking about. And it wants to do the reconstruction for that particular t. So the loss function you write down is this. For various t's from 0 to capital T, and for various God samples and simulated xt samples, you write the L2 loss, the L2 squared, L2 squared loss between the prediction of the neural net about the best reconstruction according to the neural net and the real x naught. And at all t's, the optimizer is the conditional expectation, and the reason you don't have a different neural net for every different t is because you want to borrow statistical power between the t's. So that's mathematically you don't need to do this. Practically you do this. Okay. So this is what you do. And if you have that, that's all you need. As I discussed earlier, there are three sources of error here. So one is that, you will write this L2 squared minimization loss function. You will pick a neural net architecture. You will collect a bunch of samples. You're going to minimize it. There's going to be some error that you're going to be making. You're going to run a discretized reverse SD. Okay? And finally, you're going to not initialize that P node, but you're going to initialize, sorry, this would be XT, sorry. XT will be initialized the Gaussian distribution as opposed to the real PT distribution. But as I was saying earlier, you can quantify the result of all the sources of error and understand the impact of all these errors to the sample distribution limit. And I think, this kind of like summarizes the background on diffusion models. Let me see. So here's the summary. This is the forward process I'm thinking about. This is the reverse process. One is driven by running motion, the other one by reverse time running motion. I did say all that. This is the example with like variance d at time t that I was showing you before. And lastly, there are variations to the theme. Often in practice, people use the so-called variance preserving SD, which is this one. Right? So, this one sort of like mixes between the X node sample and the Gaussian sample with weights that was, total energy sums to 1. Okay. So in particular, as t goes to infinity, this converges to not the variance exploding, but like the variance 1 Gaussian distribution. The SD for that is this guy. Similar to before, except there is like a negative drift. The reverse process is also similar, but it also has this negative drift. Of course, as well as the score function drift. And as exercises, this is a course. I can show the slide later so that you can. So I'm asking you to show that the distribution at time t. This distribution, the distribution of this is the same as the distribution of this, as well as the distribution of that. And here, to show that the distribution of this and that are the same, again, you're going to use Fokker-Planck. To show that the distribution of this at time t is the same as that, you also have to use Ito's lemma. I don't have it here, but look it up. It's a very cool lemma. So use Ito's lemma, you use Ito Fokker-Planck, and you can derive this. And this is the summary of the background of diffusion models. Long story short, let's remember that this is all you need to be able to run the reverse process. So you need, for all t, you need a function that takes as input an x and a t, and does a good approximation. Does a good approximation to the condition of expectation. If you have this, you can run the reverse diffusion process. Yeah? This is what we should do. Okay. And now I'm going to talk about low quality data. And in particular, I wanted to talk to you about how to train diffusion models when you don't have good data. For all the reasons that I mentioned earlier, my main motivation is for scientific applications, such as plot and folding, astronomy or MRIs. But but there are other aspects of as I discussed earlier, for why you want to be able to train diffusion models using corrupted data. So I wanted to first talk about how to train a diffusion model that samples good samples when you only have access to bad samples. All right. So in particular, this is similar to the MRI thing, right? So imagine that the data that you want to train a diffusion model that outputs good MRI images, but you have a lot but bad MRI images to train them. You never saw good samples. You just never saw a good sample. You only have a lot but bad samples. Right? So in particular, sorry, I have flipped tabs. I'm going to be doing that a lot. But the semantics are still XT refers to the right XT, but I'm just showing my think of the mirror image. Just mirror this image. So a couple of things I still have my noisy sample. Nature only gives me samples from some noise level. Nature does not give me samples at 0. These were never seen. All observed samples are from XTN, and of course you can simulate everything onwards. Again, I don't have access to any clean samples. But I still want to train a diffusion model. So I'm almost, we have 15 minutes.
Okay. Not very precise.
Right, so in particular, I captured any sample xt for t bigger than tn. Tn is t nature, t nature, and above I can simulate samples. I don't have anything smaller. So in particular, xt can give us a gold sample which I never saw plus a ton of variance, or I can see it as like a noisy, already noisy sample with like a little bit more variance. So these are two ways to sample an XT, and this is how I can simulate it because I only have access to XTN. But since this also came from some X mode, whatever, you know what I mean. But to train a diffusion model that samples good data, I would like this, but for all t's. Both the t's that are above the t nature, but also the t's that are below t nature. Right? So I want the denoiser for big t's, but I also want a denoiser for small t's that I never saw. So what am I going to do now? Like, how am I going to train my denoiser? I'm going to train a denoiser that will take a sample better than I ever saw and reconstruct the samples that is even better than I ever saw. Okay? So I don't have access to these things. I cannot train these things. But even here, I want to train a denoiser that takes a sample that is noisier than the one that I saw. And it reconstructs the super good samples that I never saw. So both tasks are not easy. But one of them is harder than the other. So as it turns out, this is not too hard to solve. And let me explain why. So let me treat these two cases separately. Let's try to find a denoiser that is going to take a super noisy sample, so above the nature even noisier than the nature, and try to predict X naught, like gold sample all the way to 0. Yes? So how do you do that? There's a nice way you can do that. Remember that XT has the same distribution as X naught with a lot of noise, or XTN with a little bit of noise. Right? Well, that's also true. Right? Also remember Twilly's formula. If you have two random variables, like y is just x with some noise, then if you want to reconstruct x given observations of y, Twiggy's formula tells you that it says that the score of y is just the denoiser of x given y minus y over the extra values that you added. This is Twiggy's formula from earlier, written more generally. It says that, right? So it says that for any other values connected this way, the score of this variable is just the denoiser of this given that, some corrections. So now what can I do? So here's what I can do. I can write Twiggy's formula looking at this equation, and I can write Twiggy's formula looking at the bottom equation. So I can in particular look at the score of the xt random variable in two ways. One, in terms of the denoiser of x naught given xt, but also in terms of the denoiser just from like t to tn. So which one of the two do you prefer? Do you prefer this guy or do you prefer that guy?
The choice.
But we have no choice, right? This you can train for, because you have samples from xtn, and you can simulate samples xt. So this, you can write a loss function to get access to this guy. But the moment you get access to this guy, you get access to this guy. And if you have access to this guy, that's all you need to run the reverse. You can also get access to this guy. You get access to everything you want. Yes? So this is the idea. We call this double Twiggy's formula. Okay, so putting this together, you get that if you can estimate this, you can estimate that, you can estimate this, you can estimate what you need. So you can write this loss function. Okay, so like you pick for all times that are above Tn, you get a sample that you have access to. You simulate a sample of higher noise. And this is the functional form that comes out of this, right? So this is the optimal solution of that will be exactly this, because of this formula. And effectively, right? So you basically the optimum of this is going to be this, and because of this formula, then this is going to be that. This is what I did. Is everybody with me? So this is not a big deal. It is not hard to solve. But by exploiting this, two ways to look at the score as a denoiser to xtn or the
Very neat. Very neat.
Yeah. So this is good. The bigger problem is talking about the imaginary world. Like before, we were talking about like an imaginary x naught that we never saw, but we did see the xt. Now we neither see xt nor x naught. So what do we do about that? So we want the optimal denoiser of xt t smaller than tn to x naught, to 0. We don't have access to the samples. We don't know what loss function to write down. And here what we recommend doing is to exploit certain martingale properties that are satisfied by our diffusion process. Let me explain what I mean. Okay, so this is a mouthful, so let's actually, let me show you a picture before I actually give the definition. Okay. I'm going to be talking about denoisers that are self-consistent. What do I mean by a denoiser being self-consistent? I'm imagining the following experiment. I'm going to give a denoiser sample to my denoiser, and I'm going to predict there's going to be some because it's the conditional expectation. So I can, at some t, I ask my, I give a noise sample to my denoiser, I get some prediction of its noise. So it's one thing I want to do. The other thing I want to do is I want to run the reverse diffusion process, treating this as the conditional expectation. So it's going to be some noisy path down to some xt prime. And then I'm going to invoke the denoiser. And I'm going to get, starting from here, if I do this random path, I'm going to get this guy, and I'm going to invoke my denoiser. Of course, it's going to be less layering on that, because, it came down to a t prime closer to 0. So there's going to be less noisy samples. Then this is another stochastic path. It gave me this picture, and gave me this denoiser sample. And out of all possible, sort of like, consider all possible paths down to t prime, and all the reconstructions, average them, average all the reconstructions from t prime to its nodes. I want this and that to be close. This is what self-consistency means. It means that if you denoise a noisy sample in one step, versus treating this denoiser as, dictating what the score function is, and running the reverse diffusion process and denoising from like a closer, from a t prime smaller than 0, and averaging the results. I want the two reconstructions to be close, right? So like the reconstruction out of a higher time t to be close to the reconstruction from a lower t prime, from the random sample that you would get starting at xt, if you run the reverse diffusion process, treating h theta as the score function of the reverse process that you use in the reverse process. This is what we call self-consistency. Let me now come back to this slide.
It looks like what in statistics, an unbiased estimator or something like this.
It's basically the martingale property that
property.
your reverse diffusion process ought to satisfy.
Very good.
Yes? So, here are two definitions for whatever. So, you have a denoiser x theta. I'm going to call this denoiser consistent with the kernel that samples x prime from x if the outcome of linear denoiser at given input time t and picture xt is the same as if you apply the kernel to get an xt prime and then apply the denoiser at the lower time. I want the expected reconstruction at time t prime to agree with the reconstruction at time t. So that's what I call a denoiser consistent with kernel. And self-consistent means that if I pick the kernel to be the reverse diffusion process dictated by h theta itself, right? So the denoiser is self-consistent if it is consistent with a conditional distribution defined by running the reverse diffusion process of this sample down to time theta. And sort of like the little theorem you can show, which we showed in some news paper a few years ago, is that if you have learned the score function from teenager and above, which I already showed you how to do using double twos formula, and you're also self-consistent, and you're also actually missing something. You're also a conservative. H theta defines a conservative fit. It's a gradient of some function. Then you have learned it everywhere. So if you learn it from a certain point and above, and it also satisfies this martingale property, then you have learned it everywhere. In fact, in reality, what you need is that, in fact, you only need to learn it at a single time, only at an open set of images. And if you're self-consistent, you have learned it everywhere.
So you only accept collaborators whose family name starts with D?
Yeah. And German observer is also Greek. Three Greeks and one Israeli. But we'll see some counter examples later.
Okay, we're waiting to see the counter example.
So basically, like, what comes out of this is that you know, you add like this double tweety, you know, the loss function I suggested earlier using double tweety, that would enforce that you will learn the right denoiser for t's that are bigger than teenagers. And then you also have this self-consistency loss term. How does it look like? You pick a time above teenager. You pick another pair of times that are nearby each other. And then, you know, like, sort of like, you know, this is above teenager, so you can always simulate it. You have access to this thing. From this, you can run the reverse diffusion counter something prime. You can also write it, and you can ask the denoiser to make a prediction there at this thing running. And then you can take another little epsilon step. So the reason we only do it locally is because simulating the reverse is an expensive thing. So we only want to make like a local step there and ask for local self-consistency, and that's enough. So right, there's three samples here, like one that you have access to, one that you can simulate running the reverse diffusion process, and another one that you can also simulate by doing the few steps. And you're asking for the self-consistency between the first simulated and the one that is a little bit further out, further down T. And if you do that, you can train, is the claim that the mathematical claim is that you can train a diffusion model without access to clean gradient. So here are some, let's say, some practical figures. So here we compare it to what people do in practice, which is...
Here is the category.
Yeah. So here we basically, on different data sets, CFAR, SLFA, and investment, we trained, using this consistency approach and without a consistency. If you don't want to do, if you don't have a, basically what people do, what people do typically is that, like, if you don't have access to clean data, you're just going to run the diffusion process and then just do in one hop, just start with this noisy sample. Okay, so that's going to truncate something. And you do see some improvement in the loss. I mean, in theory, this would be amazing improvement. In practice, there's some improvement. Right?
Consistency beats what is that?
Truncated sampling. Truncated sampling is like, like I go down to whatever noise level that I have and I output that sample. So here, at different noise levels, we plot like how good in some measure accepted how good the sampler is. And we compare sort of like different noise levels in the sample. So here, we add these are some comparative studies to show sort of like the impact of how much noise the samples have, and what happens if you do consistency loss versus if you don't do anything. And the trend is sort of like, if the noise is not too bad, then doing consistency effectively has the same effect as if you have zero noise. But eventually, you pay for it because the math holds for infinitely many samples. Over here, the finite sample size, and it will be hit by you know, the mathematical theory is for infinitely many samples. Like you have a lot of samples, you can do this consistency in lots and learn them all. But eventually, you know,
when data becomes larger, the
larger
rise of the curve will be.
And the other cool thing with training on noisy samples is that you solve this memorization problem also I got before. So here we're comparing a model that is trained without any noise added to the sample versus a model that is trained with noise added to every sample. And we ask the following question. We ask the model to train the sample, and then we look at the closest sample in the training set. And we're talking about the distribution of similarities between a sample, like a generated sample, and a training sample. And similarities go down if you train noisy samples versus if you train clean samples. This is the point of this one. The other distribution of similarities if you train only on noisy samples, and the blue distribution is where you train on clean samples, and you see that similarity scores go down. You produce newer samples, like newer samples versus closer to the training set samples. So the takeaways from this is that you beat the standard way to do it. You reduce the memorization, but for the same sample size. Of course, as the noise goes up, your performance starts decreasing. And I'm going to wrap it up here. So we're very happy with this, but there are certain challenges, right? Like you have the challenges that I talked about earlier, that eventually your performance will go down. And the other challenge is that it's quite expensive to train these models, these consistency-based models, because if you remember, the way the loss function was written down, to compute the loss function, you have to do a lot of simulations from the model that to take the way it's going to go is that you're going to write the loss function. Then for whatever model you're at, you're going to do a bunch of simulations of the reverse process. For every gradient step, you need to do a bunch of simulations of the reverse process, and that's expensive. Without a consistency loss, you don't need to, your loss function is your loss function. But with consistency, there is some self-referential aspect inside the loss function, right? That the loss function that I'm minimizing requires me to simulate samples from the reverse process that is indexed by this theta, right? So I'm going to be running a gradient descent procedure, like theta t plus 1 equals theta t minus the gradient of the loss function. But the loss function requires simulations that depend on the theta t that I'm sending out right now. This is a stochastic process, so it's an expensive thing to do. So what I'm going to do in the next lecture is I'm going to talk to you about how to leverage these ideas together with if you have access to a small number of clean samples. So the realistic scenario here is that it's not like you might have access to a small number of good samples and a shit ton of bad samples. What happens if you put together the good samples that you have with the large number of bad samples that you have? Can you get the best of both worlds? Like, can you do better than the standard pipeline, which is to throw away the bad samples? Like as I was saying earlier, yes. The standard pipeline is to throw away the bad samples and only keep the good samples. I argue that bad samples have information in them. What are bad samples? As we discussed earlier, bad samples have a lot of information about like higher order. If I look at the blurry image, it has a lot of the, a dog is jumping over a fence. Okay, I don't see the details of the dog. I don't see the details of the fence, but I do have a lot of information. There's an interesting action taking place in the image, right? Why throw that away? That's what I want to ask. Right? Like the consistency suggests that, even if you don't see any clean samples at all, in principle you should be able to learn the distribution you're looking for. The bottleneck is, certain practical aspects of, it being expensive to write down the loss function, as well as sort of like certain statistical problems from, the fact that you have noisy samples as opposed to clean samples. But what I want to do in the next lecture is to tell you about like how to, combine a small number of clean samples with a large number of noisy samples to get state-of-the-art models for images and proteins. Effectively, like if I want to preview what's going to happen is the following, right? So like noisy samples, why are they important? Because they have a lot of information about higher order coarse content. Like noisy samples have coarse content. Clean samples are important for high frequency information, like texture and stuff like that. Now, the good thing about low frequency information is that sort of like one sample is a lot of samples. If all I care about is high frequency information, I can take one big image and create little patches from it. And effectively, these are a lot of close to independent samples. Okay, so somehow like having access to a small number of clean samples gives you a lot of samples for high frequency training. So you want to use like a lot of bad samples because like coarse information. Coarse information has a long-range correlation across the pixels of the image. So that's why you need a lot of samples from coarse information. But when it comes to like frequencies, like high frequencies, a small number could be enough to train a good denoiser. And in fact, here's a empirical justification, and I'm going to close with that for why I'm saying this. So one thing you can do is you can train a denoising model on a lot of samples, and look at the neural net that look at the neural net that results from training the diffusion models. Again, as I told you, it's related to this denoiser. And you can look at what the denoiser does to predict a particular pixel in the image. As it turns out, for the higher the T is, the more global information. Like you can inspect the denoisers. You can inspect the like you can train. Like imagine training a denoiser on a shit ton of good data. Okay, so you have a lot of good data. You train a denoiser, and then you inspect what it does. As it turns out, for high T's, to predict the information in a particular pixel, it's going to be looking at a lot of stuff. For low T's, it's actually very local, the denoiser. There were no constraints. Like this is what empirically happens if you train a denoiser. Denoisers, for low times of the diffusion process, they're very local. To predict a pixel, they're going to look at a small radius of pixels around it in X. Right? So like to predict X node at location I, the denoiser is going to be looking at, like XT in a small neighborhood around pixel I. And the size of the neighborhood depends on T. If it's a super noisy image, and I want to predict pixel I at time 0, I'm going to look at the global information. But if it's a not super noisy image, think about it. Like if I give you like an almost good image, like to figure out information about a picture in my eye, are you going to look at like my hair? You're not going to do it because it's very local at low noise levels. But if my image is super noisy, to get a good prediction even at a pixel corresponding to my eye, you might want to look at much bigger radius. For example, there is certain symmetry with my other eye and things like that, right? That you have to take care of. But the clearer the image is, the more local the denoisers are, which justifies my intuition that I try to convey, that we have recently explored to get the state-of-the-art models, which is that if you have a small number of clean images, they go a long way towards giving you a lot of examples for training these high-frequency denoisers. And if you have a lot of bad images, they go a long way to giving you advice about interesting coarse phenomena that happen in the real world. Okay? So these are the two things that I want to exploit to train state-of-the-art models from a small number of clean samples and a lot of bad samples. So I'll close at this. If there is interest, I can show you the consistency proof. I had prepared it, but I ran out of time. Or I can just post the slide, slides for the consistency proof. It uses Ito's lemma and forget ground, and it's over here. It's not. But this is it for today.
So, if you have many good data, would the model be increasingly better, or there's a limit? Even if you give too many good data, it stops somewhere, producing better images?
It depends on the distribution. If you notice in Iraq, one sample is enough. Right? It really depends on the distribution. If it's in Iraq, one sample is enough. If it's the Gaussian, the more samples you give me, the more accurate it becomes. So even just between Iraq and Gaussian, you see you can get both behaviors. But I guess empirically speaking, more data is always better. So, the world is not a bunch of events. The world is interesting. So, yeah.
So if you are able to characterize precisely the quality of any sample, you would advocate having a distribution of the quality, which is basically the number of samples should be proportional to their quality or something like that, or inversely proportional.
Interesting question. Yeah, so next time, kind of in the middle of, I think this is what you're asking for, and I'm going to talk about this a little bit. After I develop a theory of how to use samples of different qualities, I can run experiments of this form. This is kind of a version of an experiment you can run. Train a model of only clean images, or percentage of clean and bad at different levels of badness. Right? You can see various levels of quality and compare. Right, so here I pick a size n for my data set, a fixed n, and I say, okay, what happens if I have 90% of n, but all clean, versus, for example, I don't know, 50% of n clean, and 50% noisy at this noise level, or that noise level, this, and then compare the various qualities. And then you can start thinking about trade-offs between, you know, like how good, you know, what is the exchange rate between, you know, like bad images and good images. And you know, like for example, here I talk about this example, right? So I'm comparing bad images at noise level 0.2 and clean images. And here I have like 70% of N clean has worse performance than 50% of N clean, plus another 50% at that noise level. So, you know, this suggests that, you know, like, I have like a linear exchange rate between bad and clean. I can write the equations in this form, that, you know, like, I should be paying more for 50% N clean plus 50% noisy, because I get better quality from that mixture, versus 70% N of clean. So that, you know, so if I were to pay, you know, price P clean for clean images and P noisy for noisy images at this noise level, I should be paying more for this mixture than that. And I can derive equations for like how these prices would be connected. And you know, like we fooled around with this. For example, like, and you know, you can get pretty tight bounds in the exchange rates. So for example, like for noisy, for variance 0.1, for standard deviation 0.1, by comparing various entries in this row with like entries in the clean in this row, we get that the exchange rate should be sitting somewhere between, you know, like where the dollar is to the euro. And for like 0.2, you get some other, but you know, you can get you know, exchange rates between noisy versus clean. If you want to have like a auction house or like people contributing clean and stuff, you can do
as in terms of global efficiency of the system. But this seems to change the game usually, because the usual thing we think is that good data is very, very precious, and there are in many cases bunches of slaves around the world who want to take the data.
That's exactly actually, yes. And in fact, you know, like when I talk about proteins, I'm going to describe kind of like a story of what happens now versus what we can do. So in proteins is very stark, right? Because to get the fold of a good fold, like a real or close to real fold of a protein, it's a very painstaking process. You have to do extra crystallography, there's a ton of work and a very expensive process that goes with it. And we have like, you know, maybe a couple of 100,000 such good databases. On the other hand, we have a lot of bad data points. How do we get them? We get a protein sequence and we push it through AlphaFold, and it provides a fold together with some confidence. Like also it self-reports some confidence. These are easier to access bad samples. So next time what I'm going to discuss is how current state-of-the-art models, like the protein model that I told you earlier, only uses the small number of samples that are good. While what we can do is to also use the bad samples using our methodology. And the result of that is actually state-of-the-art models for protein folding.
Yeah, aren't you making the hypothesis that your bad samples have the right low frequency information?
Right, so the recall in applying sort of like my theory to proteins is that why the heck would AlphaFold make additive Gaussian noise errors? Yes, like, it doesn't. Okay, so who knows what is the error model of the mistakes that AlphaFold makes? Most definitely, it doesn't like jiggle all the atoms by additive Gaussian noise in the predicted fold. So here we use, and you know, again, to give you a little bit what will happen in the next lecture, we use the following interesting idea. We say, okay, like, you have a noisy sample, the noise model is whatever. Who the heck knows what is the noise model? take that noisy, who knows what sample and add to it extra additive Gaussian noise, that is closer and closer to behave like a clean sample with additive Gaussian noise. Because Gaussian convolution contracts distribution distances. And I guess what I'm going to, okay, just to preview, what I'm going to do next time is I'm going to run, let me run it now. So I'm going to compare, I'm going to run this whole game with you. Okay, so here is a clean image of my colleague again. The next one is a blurry image of my colleague. The blurry image of my colleague is definitely not the original image with additive Gaussian noise. Right? Like I've shown you what happens to my colleague if I add to him additive Gaussian noise. But this is not it. This is like a Gaussian blur. But let me add additive Gaussian noise to both of these images and ask you to tell me if you can guess which of the, I have added, what I did here is like I took the images, I added Gaussian noise and randomly permuted it, and now I'm asking you to predict which one came from the blurry and which one came from the clean image. Can you guess? Did this come from the blurry plus noise or from the clean plus? Like, if you have to guess, which one came from the blurry?
You have to make as votes.
Yeah, okay, so who thinks that this came from the clean image plus noise? One person, two people, three people, four people. Who thinks that this came from the clean image without the Gaussian noise? Okay. So, the majority thinks that the right one came from the clean, and indeed, I mean, if you look at my screen, it looks better, but here there's extra noise by the projector. This came from that, and this came from that. Okay? So let's look at even more noise. Now, can you guess who thinks that this came from the clean image plus noise? Who thinks that this came from the clean image plus noise? Okay, again, the majority thinks this one. Let's see what's the truth. Majority wins, yeah? How about if I had a shit ton of gas? Can you guess? That's much harder to guess, yeah? Okay, so you have a proposal?
The left one is
Left is a clean? Okay, so let's see. I don't know. Yes.
Good.
But
most are not taking bets now.
it's very hard, right? And I mean, the mathematical fact underlying this is that sort of like, if I take two distributions, P and Q, and look at their TV distance, and look at P convolved with Gaussian, and Q convolved with Gaussian, the TV distance contracts, right? So like the TV distance between P convolved with the Gaussian and Q convolved with the Gaussian is like the TV before the convolution over sigma. Upper bound. So the more Gaussian noise I'm adding, the closer they become. Which suggests the following, right? So I have this alpha fold, who knows what error model distribution. If I add some Gaussian to it, it behaves like a clean sample with this Gaussian noise. So now I can apply my framework that only works with Gaussian noise. And this is what we're going to do. Okay? So that's that's kind of like summarizes what the plan is. Yeah.
Is it useful to include model-generated images to train your model, or it doesn't even make sense?
I guess yeah, from various viewpoints, like from the viewpoint of like, okay, like if you can take the samples from your generated model and treat them in the same way as noisy, but who knows what samples, and treat them this way. there's also like a way to view it as a bootstrapping, you know, the details matter here, so for whether or not this is reasonable. All right. Exploits the locality of bias